Alright, grade 12s. I'm just going to warn you before I start this video that I'm going to probably upload this for Monday morning, but it's actually Sunday night. Very late for me right now, but I'm busy tomorrow, so I wanted to get this uploaded, or at least recorded before morning. So if I yawn and stuff like that, that's because it's past my bedtime, okay? Alright, so here's the deal. Something weird, okay, for you here today. We have seen, okay, and I'm just going to remind you, we have seen that two sources, okay, will produce interference, and we spent a lot of time going through this whole interference thing. Okay, so we understand this very well, that two sources or two slits will produce interference, and we've seen two source interference, we've seen double slit interference, all good, okay? But here's a weird thing. One slit can produce interference. How is that possible? Because you'd think you would need at least two sources to have interference. Well, here's the deal. You do have two sources. In fact, you have more than two. Because according to Christian Huygens, we have something called Huygens Principle, every point, okay, on a wavefront is a point source, which means like dotted along every wave is several point sources, okay, and they can interfere with each other in a single slit, okay, and that's the deal, and I'll show you that in a moment. But before I do that, I just want to prove it to you. Here's some photographs. So this is a photograph of single slit interference. Here you see at the top, that's one slit, okay. Now that is a node, okay, and you see another one here, node. These here, I'll color them like yellow, if it'll let me. What's lagging or what? Here. That and this. And by the way, this big one here, these are antinodes. There's really no mistaking it. It's interference from one slit. Okay. Now, if you look at the double slit pattern, this is our familiar pattern. Now, here's the thing. These are to scale. Okay. Now, for the double slit pattern, the nodes are closer together. So just let me point that out. That is a node for the double slit, and here's another one. Okay. And in fact, there's another one. Okay, another one there, and so on. So here, these are all to the same scale. If you switch from a single slit to two slits, and keep the slit size the same, you'll find that, like, if you really look carefully here, there are two patterns. This, in the circle of the big circle here, and this guy here are the same size, okay? And so those 5 antinodes that you see in the double slit pattern, the second line, okay, of interference, that you can clearly see the single slit pattern is there too, and they're superimposed on top of each other. All right, so this is with a laser. This first one, this is with a laser beam. This one here is just with regular light source. Okay, normal light. Okay, and what we see here is this is a double slit pattern. Okay, I'm just going to zoom in a little. This is double slit. How can you tell? Well, we see two patterns here. Okay, we see a very fine series of bars. So here I'll use my rainbow color. These little bars here. Okay, these are double slit nodes. Okay, however, this, oh, I see, it is highlighting, you just can't see it very well. I'll use red. So this dark, big, huge honkin' dark area here, this this, and this. This is the weird part about it. This is, and these guys are single slit nodes. So we can see that when you do double slit interference, you're actually seeing two interference patterns. Okay, one of them is single slit because each slit acts like a single slit, but also those two slits interfere to produce the double slit pattern. Now this, if you zoom in on the midsection of this diagram here, you zoom in there, okay, this is what that looks like. And there, actually, you go back to my rainbow just to be consistent. Here we see that is delta X, okay, your double slit nodes, okay. So you can see that like both patterns exist together, okay, on the same picture. And that makes sense because, like, you know, if you shine a laser through two slits, you're going to get a single slit pattern because they behave individually like single slits. They'll be right on top of each other. But because they will also interfere with the double slit interference, the two source interference, we also get another pattern of nodes and antinodes superimposed on top because there are two slits. Okay, so one slit would be like this, but you wouldn't get the fine pattern of bars. You would just get the big sort of, you know, this whole area here would not have a fine pattern of bars. It would just be shaded in solid. Same with this guy, same with those guys. Those are single slit antinodes, okay? And that's what you're seeing in this top line here that I've colored in blue. And when you switch to double slit, the double slit pattern gets superimposed on top of the single slit. Now, three slit patterns and four slit patterns and so on, they're a bit different, but you can always see the single slit, that first pattern there somewhere, okay? But anyway, we're only going to do 1 and 2 slits. We're never going to do more than that, so don't worry about 3, 4, 5, 7. Don't worry about it. I don't know why they skipped 6 either. You could legitimately have 6 slits, right? All right, so now let's zoom out of here. How does this work? How could you get interference with just one slit? Well, Huygens said that every point on a wave is a point source. So what he's saying is that these waves, here I'll draw them the same, they have, like, every point on the wave is a point source of waves. So those point sources can interfere with each other on the other side of the slit to produce interference. We're going to call the width of the slit W, okay? And believe me when I say you can get interference through just one slit. And your book goes through this derivation, but I don't want to waste your time, okay? We spent a ton of time deriving, like I personally spent a ton of time showing you the derivation of the double slit formula. If you're curious, go ahead and read the textbook, but let me give you this, the gist of it, okay? The way it works is like this. All right, let's say we had 12 point sources, okay? So if we take, here I'm going to just take color red here. If I color that one in, and also number 6 in, okay, that's one is from the top half and one is from the bottom half of the pattern. If the path difference is half of a wavelength between number 12 and number 6, then it will also be half of a wavelength between 11 and 5, and between 10 and 4, and between 9 and 2, and 7 and 1. And if that happens, I will get a dark spot, okay, and when exactly this condition is met. In other words, when the path difference, and just like the double slit, the way it works is they construct an angle here, theta 1, and you'll find that that's equal to this theta 1. Now we did that before, okay, with the double slit pattern, so I don't want to rehash all that, but that's how it works. Now, you can also get bright spots. Bright spots occur when number 12 and number 6, okay, are like 1.5 wavelengths apart, okay? So if this turns out to be 3 lambda over 2 equals the path difference, then what will happen is you get that same path difference you get the same path difference like in pairs all the way up. And in that case, you get constructive interference. Anyway, I don't want to go through the whole thing. They go through it in great detail, several pages in the book. But like, I just want to summarize these things for you, okay, and show you how it works. Okay, so as long as you understand that single slit interference happens, okay, and it happens because of Huygens Principle. So Huygens says that every point on a wave is a point source, and that's why you get single slit interference. And if you shine a laser beam through a single slit, it works every time. So here, I'm going to summarize double slit. Black. Double slit. And I'm just going to organize it like this. I'm going to write antinodes and uncle nodes. Just kidding. Okay. So, what's the deal with double slit antinodes? Okay, so for double slit, if the path difference is m lambda, okay, where m starts at 0, okay, actually I'm going to give myself a little more room. Okay, you will get constructive interference. Okay. Also, if you get sine theta m equals m lambda over d, constructive interference. Okay. And finally, x m over L equals m lambda over d. We didn't really do that formula, but you could. We didn't do the bright ones, we just did the nodes. So that's it for constructive interference for double slit, and for destructive interference, if the path difference is n minus 1/2 times the wavelength, you get destructive interference. Sine theta n for the nodes, right? N minus 1/2 times lambda over d. It's a formula we derived. And finally, xn over L equals n minus 1/2 times lambda over d. All right, so that's for double slit interference. Now, for single slit, that's really all you need to know, right? Single slit, it's a little different. So let's talk antinodes. Okay, and nodes for single slit. And actually, I'll do this. Okay, same. So now I'm going to zoom in, so I have a little, I can write a little smaller. Here, if the path difference, it's kind of switched. M plus 1/2, okay, times lambda. Okay, you get constructive interference. Now, sine theta m, again for constructive interference, would be m plus 1/2 lambda over w, where w is the width of the slit. See how similar it is, right? But not quite the same, especially for the antinodes, it's a little different. Oh, before I get away from this, the spacing delta x equals L lambda over d, right? That's important. Okay. Now finally, here I could do this. We use y for single slit, so ym over L equals m plus 1/2 lambda over w. Okay. Now you should kind of get what these things mean. I'll maybe, you know, it's ym is the distance from the perpendicular bisector, the center, right, to the antinode, to the middle of it. Okay, so I'll show you on the diagram above. Now for the nodes, you get this, path difference equals n lambda, okay, like that. It's kind of switched from the other one, but it's a little bit different. It's plus a half, not minus a half. Sine theta n equals n lambda over w. Okay. And finally, yn over L equals n lambda over w. And the spacing of these guys, delta y, equals L lambda over w. Okay? Now if you look, it looks kind of astonishingly similar, the single slit and double slit, but there are differences. Oh, I'm sorry, that should have been a delta y, not delta y, not delta x. Okay, and that's the spacing. And we'll talk about these variables in a moment. L means the same thing, lambda means the same thing. It's just W versus D. W is the width of a slit. D is the distance between the two slit centers for double slit interference, right? Okay, so one more thing, note that the central maximum or antinode has a width of 2 delta y's. Okay, you'll notice it's wider in the middle than all the other antinodes in the pattern. Okay, whereas in the single slit, double slit pattern, they're all the same. All right, so let's go to these pictures and let me show you what I mean. Okay, so here, let's use this one. Okay, so I'm going to draw a line. We'll make it, maybe we'll make it green. I'm going to draw a green line down the middle. And the green line I color in that central double slit antinode. That is the bisector, right? Bisecting the pattern in half. Okay, so in this picture, if I zoom in close enough, and I'll use rainbow, the distance there is delta x, okay? And then like here, when you're going to these nodes, that's x1, you know, like that would be x2 and so on, okay? So that's for the double slit pattern. But for the single slit pattern, the picture, the pattern itself is much bigger. So I'm going to use blue for this. All right, so here, if I measure from the center of that to my center here, that is delta y, okay? But it's also, in this case, if I go this way, that's y1, okay? Now if I measure from to the second one, that is y2, okay? And from here to here, be delta y, okay? Whereas delta x is much smaller. Delta x, I'll use red. Delta x would be that distance. That would be delta x, that little fine pattern of bars you see there, okay? All right, so anyway, now that you see the sort of differences between these two things, remember W is the width of the slit, D is the distance between the two slits if it's double slit interference. That's it. I do idea on at some point. All right, so there's your summary. Now, I have a question for you here. I wanted to show you this because this is how I got my computer to draw the interference pattern. I want to show you what, like this is double slit interference. You can tell because you see both patterns here. And I'm going to say that it looks like you're looking at this weird zebra, but that distance is delta x, okay? And then here, from this edge to that edge, and I'm going to do a little fuzzy, I won't use red, I'll use blue. So here, that and that would be a single slit node, okay? And this distance here to this distance here, the outer edge to the outer edge would be 2 delta y, Okay. Now if I go from this one to this one, there's another antinode there, sorry, another node there, another node there. That would be 1 delta y. Okay. So normally what I would do is I would print this on a piece of paper, and you would actually make the measurements with a ruler. Okay. Now I actually didn't do that. It's like I can't print it for you. Now you could print it yourself if you really want to. So what I'm going to do here is, I just got a email from Mr. L saying, looking forward to you unleashing your inner Elsa. Well, there you go. Looks like it's Thursday. Okay, so here's the deal. I'm going to give you a number here. I'm just going to work it out, and then I will let you do the calculations on your own for this. So I'll give you the measurements, but I just have to work out what they should be. Okay, so I'm going to go with green light. I'll go with one of my favorites. Okay, green light. So, okay, just pardon me, I should have done this ahead of time. I just wasn't thinking. Okay, because it's late. And I forgot that you wouldn't be able to actually measure this with a ruler unless you printed it out. So to save you that trouble, does it say what L is? 2.3 meters. Yeah, L is in there. So times divided by 4. Times. Alright, so I'm going to tell you that I'm going to erase this. If it will stop lagging on me, that'd be great. Okay, so I'm going to tell you that the distance from here and then to here. Okay, now on purpose, I've done this on purpose. Maybe I'm being dumb, but anyway, I'm going to stick with this. That is 2.81. Am I doing this right? I don't know. I think it's 2.81 meters. This is a huge pattern. But anyway, let's see if I got this right. I feel like it's not right at all. Let me try it again. So oh gosh. Pardon me. It's 2.81 centimeters. Obviously. Because you're going to print that on a piece of paper and measure with a ruler. Okay, so that was 2.81 centimeters. Make sure I'm doing 1, 2. Okay, yeah, I got it. Now, yeah, okay, I think that'll do it. 2.81 centimeters. Yeah, I'll leave that to you now. Okay, so now that I've given you that measurement, so now you have some idea of scale, you should be able to answer the questions that you see here. Okay, do not use this because you're going to get the first one right. Okay, all right, so that's it. And single slit interference. Now this is an example of double slit interference because you can see both patterns there. Okay, And like I said to you, I think in the beginning of the unit, you can use this to measure something really small, like the width of a hair. And so that's what we can actually do with this, is using interference to do that. All right, that's it for now, guys. Have a good day. We'll talk to you soon. Actually, before I let you go, if you look at the outline, we just did single-slit interference. That puts us here. Puts us there. And I didn't erase it. That puts us there. Okay. So please do that. And look what we have left. We're going to finish this week. Okay. We're going to finish the waves unit, and then we just have quantum. We'll only have 2 weeks left after this week. Quantum will only take us, about a week or so. So we should be good. We'll finish the course. All right. So guys, have a good one. We'll talk to you soon.